about fluids. So let me make sure I can operate Rasmus's computer here. There we are. This is more of Rasmus's work, and more and more. Here we are. So I'm going to start with fluids, and one of the major things with fluids is all the terminology we had. And yeah, so I have basically the list of the terms here. A lot of the stuff is just things that you need to remember. So I just put the terms here. When we really get to the equations and doing the math and stuff, this comes to what we talked about in the learning objectives. So initially we had pressure, which is just force over area. And while that's a simple concept, you can do some pretty cool things like we showed with using the hydraulics to push up a car, just by comparing the force over area of two different areas on the same liquid fluid. Another thing we discussed was the buoyancy, and that's the one thing I'll draw up here on the board. Can you see? Can they see me on the board? Can you guys see me? Rasmus, how do you get?
Yeah, we can see you.
All right. Okay, so if we look at basically, we look at just some water here, and we're just going to have this in a some type of bucket. If we're here at this point right here, we could just imagine this water right here. And if it's just sitting here, nothing's happening. So what this means is we must have this water volume here. This water we're going to call mass of the water times whatever gravity. That's the force going down. And this is just water, so nothing is really being moved. So if we have this water forcing us down, we must have another force balancing that, right? Because water is at equilibrium, it's just sitting there. So this is our buoyancy force. And this really looks kind of pointless when we just have water sitting here, just water in water. There's nothing really special about that. But where it becomes really interesting is once we remove this and we don't have water here, but we have a box of some given density, we're still going to have this buoyancy force, but then we're also going to be having the weight of the box pushing us down. So we know what our buoyancy force is, and that's what we have here on the learning objectives as the mass of the fluid times gravity. And that's whatever we're going to displace. So because of that, that's how we can use this buoyancy to push us up versus whatever object we have here. And if you look at the notes that we had from this lecture, we actually looked at like an iceberg. So we had the iceberg, which is basically our volume here, our volume times our density, which was our mass. So that was pushing us down. And at the same point, we were removing this liquid. And the liquid we were removing, that gave us our buoyancy force. So balancing those two out, you can figure out how far something is going to go down by the amount of water that's being removed. Are there any questions on the buoyancy? Okay, so that was the second thing we learned. And then the last thing we learned, and really the most applicable, and which we really use in fluids, is the Bernoulli's equation. Now, I went through a derivation of it, but what we're really interested in just the end result. And the end result we see there at the bottom, we have a pressure term, a density times our gravity times height terms, and then our velocity term. And whatever we have at the beginning, we're going to have at the end, provided we don't have any friction losses. I think we don't have any problems where we involve friction losses. So that really looks like a straightforward equation, but there's a lot of things we can do with that. And I'm going to go through two examples of operating the Bernoulli's equation, basically by going through a problem we had on the exam in the previous years. So if we look at a 2019 exam problem, what we have here is this cylinder where we have water going through a pipe, and we know some things about this pipe. We know the initial radius, which is going to be R, right at the beginning at point A. And we also know the pressure there, and we know the velocity. So that's the information we're given. And then further down the line, we have some type of, they call it calcification. You could also have rust, and this has actually happened to me couple months ago. So this is a realistic problem. And what that's going to do is it's going to restrict your pipe. And what this means is, in at least the way this problem put it out, you're going to have a pipe diameter of 3R over 4. And especially when it comes to the exam, don't get caught up on the, the weird formatting, because sometimes there may be something that's weird formatting. We have 3R over 4. It would make a lot more sense to call it 3/4 R, right? So realize that, sometimes the formatting may seem a little odd, but just don't get caught up on that. So we have this initial radius of R. A little further down the pipe, it's 3/4 R, and because sorry, I'm just trying to read the comments. Because of that, we're going to have a change in the pressure and a change in our velocity at point B. So that's what we're going to try to figure out. What is our pressure and what's our velocity at point B? So when you have a problem like this, it's very clearly, a fluids problem. The first thing you want to do is look at Bernoulli's equation. So let's bring up Bernoulli's equation. And here's what we have. So we have these terms, and we need to look at all three of them and see if there's anything we can cancel out right to begin with. So one term we can see is we have this height term. And if we go back and we look at our pipe, we can see it's basically just vertical. So because of that, we're not going to have any change in height. So that allows us to eliminate the height term. So we have a much simpler equation here. And we also know some parameters. The first parameter we know is we know our pressure at A, and we know our velocity at A. And we're looking to solve for our pressure at B and our velocity at B. But let's just try to get this in terms of our pressure in B. So right here, we did a little bit of algebra, and we've isolated our pressure at point B. Like I said, we know pressure at point A, and we know our velocity at point A, but we don't know our velocity at point B. So after this, algebraic rearrangement, we have one of our terms isolated, but we have two unknowns. So when you have one equation and two unknowns, then you need another equation. So, where do we get this other equation? And one thing that we can do a lot in fluids, and I probably didn't, push this enough in class, is we can use the conservation of mass, or the continuity equation, if we divide that by time. So we need this extra equation, and the continuity equation is basically, our mass flow rate in has to equal our mass flow rate out, right? Just conservation of mass. So we know our mass coming in at A has to be our mass coming out at B. Now, there's a bunch of different ways we can go with this, but the first way we probably want to, break this down to figure out what our masses are is to, convert this mass into a density times a volume. So for A, we can determine our density. For point A, we can, have our density times our volume, and the same for the B side. Now, since this is water just going through our pipes, the density of the water coming in is going to be the density of the water coming out. We can make that approximation. That's quite reasonable. And that tells us that both these densities are going to cancel out. So then we're just left with volumetric flow rates. Now we can break our volumetric flow rates down into a velocity and an area. Now, note here that in the second from the bottom equation, I have a big V and a dot over it, which stands for volumetric flow rate. In the bottom equation, we have a small v, which stands for velocity. So our velocity going through a given area is going to give us our volumetric flow rate. And we can do that for both point A and point B. So we have our volumetric flow rate, and now we have this this VB term, which is what we're trying to get, because that's what we were missing in the Bernoulli's equation. So now what we want to do is we'd like to isolate our VB. And if we do that, I guess the formatting changed a little bit, but you can see that our VB is our velocity at A times the difference in our area between the two. So let's bring that back up again. So we have here our areas. Now we just need to figure out, what is our area in terms of terms we know. And the one thing we were given was, the radius at point A was r, and the radius at point B was 3/4 r. So we know our area is pi r squared. And now we can use these difference in r values, to relate to our area, put them into our equation, and then that should give us something in terms of VB that we'll know. So we already know VA. We know that the pi's are going to cancel out. And then we're left with this, r squared, RA squared over 3/4 RA squared. So then we just, do the math. Our RAs are going to cancel out. And you do have to be careful here because you have that 3/4 on the bottom. You're squaring that, and it's very easy to flip your fraction around. So be very careful with this, and don't get your VA and your VB screwed up. And you're going to realize that your VA is, sorry, your V, that's not exactly right. On the left-hand side, it should be VB. Your VB is equal to 16/9 VA. So now that we know what our VB term is, we're going to put that into Bernoulli's equation. And if we put that 16/9 VA into our Bernoulli's equation, now we have our pressure at B just in terms of our VA and our PA, two terms that we know. So we can just basically take those two fractions, and they're complicated fractions, and subtract the density times VA squared terms. And you'll see, in one case you have 1/2, in the other case you have a really huge number. And when we put these two together and we keep a common denominator, we get something that's actually pretty ugly. So we get, 175 over 162, times density times our VA squared. It's an ugly number, but it's the correct number. And we're also looking to solve VB. So that would be, we solved that earlier as 16/9 VA. So from this, we have our VB term and we have our pressure B term. So then we've solved the problem. One double check you can do is to see if what you have here, especially for your pressure, makes sense. So my pressure here at PA is going to be higher than it is at PB. So you see PB is going to be PA minus some value. And that makes sense if you just think about that your force is going to be, less, force per area is going to be less as you go further down because you're going to have that restriction. So that makes sense. You are going smaller with the same amount of mass coming through there. So your velocity should be higher, and our velocity is 16/9 higher than VA. So everything makes sense from a common sense standpoint. And then we have the math to back up the right answers. Any questions with regards to this? All right. So I'll move on to another problem. And in this problem, again, we're dealing with water. So the first thing you think of is Bernoulli's equation. But let's read it through and see what's going on here. So in this case, we have this water barrel, and we're slowly filling it up with water coming in from the top at a certain rate. And it's a very small rate. It's what, 3.2 times 10 to the minus 4th meters cubed per second. But at the same point, we have a hole in the bottom of our cylinder that's letting the water go out. And we know the radius of that hole. So the question is that once this water starts building up, we're going to get it to an equilibrium. And at that point, it's going to be a certain height. We're going to have some water coming out our bottom, and we're going to have more water coming in. So obviously, as we get higher and higher, the water coming out our bottom is going to be faster and faster. But the question is, when is the point where that water coming out matches the water coming in from the top? So that's kind of the problem. And there's something you kind of have to know here, and they kind of mention it here, is that what we assume is that this water coming in is so slow that the velocity at the top of the water is basically going to be 0. And I think whenever we have a problem, we write that in there, but if it's not, that's just a natural assumption you should always make. So that's what we have. This is the information. Now what we want to do is go to our Bernoulli's equation and see, what we can do with this. So we have our Bernoulli's equation, and we know we're going to have a difference in height. That's what we're trying to solve for. And we know our velocity at the top, it was just told to us that that's going to be very slow, and we can approximate that as 0. Now we do have the pressure term at the top and the pressure term at the bottom. And you can tell at the top, it's going to be atmospheric pressure. Now at the bottom, you're also going to have atmospheric pressure. Now, if you wanted to be really precise, you could say that the pressure at the bottom is going to be, lower in height than the pressure at the top, and there's going to be a little difference there. The thing is, you're talking about air, and the density of air is about 1,000 times less than that of water. So what we can basically say is the pressure at the bottom of the tank and the pressure at the top of the tank is going to basically be the same. And that leads us to this equation we have right here. And now what we have is what I think it's called Torricelli's equation. And it just is a simplification of Bernoulli's equation, but it's just a lot easier to just remember Bernoulli's equation, break it down, and then you get this Torricelli's equation as we have right here. So we can see with this equation, we have density on both sides, and it's water. So our density should cancel out. And we're looking for the height difference, to solve this problem. So that's what we're looking for. So what we want to do is we want to isolate our height. So now we have, just two terms. We have our gravity, which we know, and we have the velocity at the bottom of our tank. And that's an unknown. So again, one equation, two unknowns. So we need another equation. And again, we want to go back to our continuity equation. So that's really, you have your Bernoulli's equation and you have your continuity equation. And those are really your two major equations when you're trying to solve fluid problems. So we need our extra equation. We go to our continuity equation. And you can see here, we had the mass flow rate at the top is going to have to equal the mass flow rate coming out the bottom. And that's what we said, we're going to hit equilibrium. So again, we take this and we determine our density and our volumetric flow rate for both sides. Now, again, since this is water, our densities are going to cancel out. And then we're just going to be left with our volumetric flow rates. Now, you could make a very simple mistake to convert these volumetric flow rates into the velocity times the area squared, as we did in the last problem. But if you look at the actual problem statement that we had, and unfortunately I don't have two slides, but if you go back and if we go back and we look at that, do that real quick, you can see we're already given our flow rate coming in. So we know what our volumetric flow rate is. It's 3.2 times 10 to the minus fourth. So when we go down here and we have our volumetric flow rate at the top, we don't need to break that down into velocity in an area because we're already given that value. So that's already known. And then we break down the other side, the bottom side, we break that down into our velocity in our area. So what I'm trying to say here is, be careful when you start going through a derivation because you don't always need to go to the end. You may have, the value before you, try to break it down as far as you can. So we have that for our volumetric flow rate at the top. And if we want to get our velocity at the bottom, we just take our volumetric flow rate divided by our area. And obviously our area, it's going to be a diameter, it's pi r squared. And we were given the radius. I believe it was 0.5 centimeters as a radius. So we know what our V bottom is. Now we go back into this modified Bernoulli's equation we have. We take this velocity at the bottom term, put it into there, and then we're going to have basically an entire equation where we have all the knowns except our change in height. So we put this, sorry, that slide should not have came in there. Yeah, anyways, if we look at the second slide, sorry, the second from the bottom, you can see that our volumetric flow rate over our area is put in there. And then on the bottom slide, the numbers are put in there, and we figured out that the height is 0.84 meters. The third equation from the bottom that should not be in there, I tried to delete that and it did not work. So anyways, ignore the third equation from the bottom. What you see, we just put the term we had from our continuity equation into our Bernoulli's equation, and we ended up getting ourselves a change in height. Are there any questions with respect to this? All right. So now I'm going to go on to oscillations, unless there's any questions in general about fluids that I should go through.
One question. You said that the pressure at the bottom was the same as for the top.
Yeah.
Yeah, could you just go?
Yeah, so that's not exactly correct. And that's kind of one of the approximations that the Terselli's equation takes into consideration. You do have a difference in pressure between the top and the bottom. And it's basically your force times your area, and you're going to have basically it's the difference in you're going to have the density of your fluid in there. So your density of your fluid in that case is going to be air, which is about 1 kilogram per meter cubed. Whereas for the water, the other term, the second term, that's going to be 1,000 kilograms per meter cubed. So your difference in pressure is going to be so small that it's basically negligible.
All right. That makes sense.
Yeah, you can also think of it from a practical standpoint. If I have a drum here, I mean, I'm going to have a pressure difference, or I'm going to have a push from my water. I guess a force times the area, so it'd be pressure with your water, but over here in the air, it's going to be so minimal, you'll never have that. Plus you'll have the buoyancy force. So it's just going to be basically negligible term. Oh, about the viscosity. Know the basics. I mean, know what the two equations we have, the Reynolds number and the other equation we have with respect to the viscosity. Yeah, it's all right. It's on the bottom of this slide, but it's not coming through. There is there's the Reynolds number, and then there's also the let me have it on my printed out slides. Right. Yeah, the pressure drop equation. So have this equation here. Our pressure drop equals 8 times our viscosity times our length times IV over pi r to the 4th. Yeah, so that is going to be, I mean, there's that equation,
And there's also the Reynolds number that uses viscosity, but just know the basics with respect to those two equations. And I'll when I send this out, I'll make sure that you have the PowerPoints that have all the information on them. Why can we use the continuity equation? I think the flow is always more than flow out. Yeah, okay. Yeah, the question is with respect to that last question right here. Sorry, let's get the, yeah, this equation right here. The thing that we say is that, where is it? Basically, you're going to reach an equilibrium. So as you keep building up that height of that water level, you're going to increase the velocity coming out of the bottom. And we actually saw that right here. So this is just a Bernoulli's equation. This isn't the continuity equation. So from the Bernoulli's equation, we can see as we increase the height, the velocity of the liquid coming out our bottom is going to increase. So that is going to, you know, keep our outlet is always going to go faster and faster as we increase our height. And we're bringing our liquid in at the same rate. So if we keep bringing in our liquid at the same rate and our velocity can go faster and faster, we're going to hit a point where we reach equilibrium. And those two forces balance out. And that's kind of what they were asking, what that height was in this question. I hope that answers that question. Okay. Anything else? Okay. So the last topic we're going to go across is oscillations. And oscillations can be, you know, a little complicated. So just a small point to make in the oral lecture, if you're following it on the board, there was one point where I went through, this should be for the damped oscillations. And I wrote this term of what X should be. And if you notice, there's a squared in the square root term that I don't think I put on the board. So I also wrote this note in DTU Learn. So just if you're tracking your notes, it's correct in the book and everywhere else, but it's just, I think when I put it up on the board, I forgot the squared sign. Just wanted to make sure you guys knew that. And with that being said, if we actually go to our learning objectives and what we were focusing on, we did have basically the simple harmonic motion. And then we had our distance, you know, anywhere within a spring, basically, you know, a function of time and this sinusoidal equation we have right here. And we also had our frequency as a square root of K over M. So, oh geez, I'll try to pick this up. So we have our energy and oscillations here of the underdamped, the critically damped, and the overdamped. And then we do have damped oscillations where we had this damping constant in front of it. With that being said, I'll go really quickly through this example. We have this figure here where we have basically a some type of mass, and we have two springs on each side. And what we want to do is just determine our velocity in terms of X. Rasmus, should I? All right. Okay, so basically, you know what? Sorry, we need to get going. I'll just record this and I'll put it on the I'll put it on DTU Learn this afternoon. So with that, is there any final questions? The computer needs to go, so I need to go as well.
That's my fault.
All right, that's just how it works. All right, see you guys. All right. Should I just end mute all?
Yeah.
Okay, I'll let you just finish it up.
I mean, that's just fine.